Hey guys, my name's Jacob Sanders, and today I'm going to be going over the PyJWT source code. This is part of a series that I am going to try and do, which is basically me reviewing the source code for a bunch of different Python libraries that you can easily pip install so that you have a deeper understanding, and I develop a deeper understanding of how the source code libraries work themselves, and maybe I'll even have videos about how, as like the next programming step above it, where you just use those libraries, what it looks like as sort of a client of those libraries versus what it looks like from like a very comprehensive view of what the entire library is. So I'm going to potentially avoid some. I may or may not, depending on the project, go through every single file. Like I could see myself ignoring files that are related to DevOps stuff, but I might even go through them, and files potentially related to testing, since that can be very verbose. In some libraries, you find that testing is like maybe 60% of the entire thing, and it's just it's good and necessary, and it's good to be aware of it, but reading through it might just be kind of a little bit unrealistic. So anyways, yeah, this is a series I'm going to try and do, and this is PyJWT. Let me start off by showing you the exact version of the library. It's PyJWT version 1.7.0. I chose this version. There are later versions out, but I chose this version because this is what I've been using. Most of them are going to probably be almost the same, but this is still a useful video anyways. So we're going to start. There's one directory inside of this. So this is the JWT library, and so if you want to import this, you're going to do import JWT, and then you're going to be pulling from stuff here. And there's one directory in it called contrib and algorithms inside of there. And I'm just going to be going in order based on this. I'm using PyCharm, and I'm looking inside of the V environment site packages for Python 3.9. And I'm going to be going through this in the order that it is here because that's going to be simplest. So what you have first is this empty init.py file. This is used to allow importing to work correctly because that helps set up modules to be like, it helps set up directories to be like ready to be imported from and whatnot. So let's go to the first Python module itself. We'll just start from the top and jump in. There's a comment which says, note, this file is named py_ecdsa.py because import behavior in Python 2 would cause ecdsa.py to squash the ecdsa library that it depends upon. All right. The next thing we have is import hashlib here. We have import ecdsa. We have from jwt.algorithms import algorithm. From jwt.compat import string types, comma text type. And then we get into a class declaration here. It is class EC algorithm, which is inheriting from a parent class called algorithm. The doc string here is perform signing and verification operations using ecdsa and the specified hash function. This class requires the ecdsa package to be installed. This is based off the implementation in PyJWT 0.3.2. Inside of this class declaration, we have a variable named SHA-256, which is equal to the SHA-256 value from hashlib. Then you have SHA-384, which is equal to hashlib.SHA-384. Then you have SHA-512, which is equal to hashlib.SHA-512. Then we have the init function, which accepts the argument self, comma, hash algorithm, or hash_alg. And then it sets self.hashalg to hashalg. Then we have the function, the method. It's not a function, it's a method because it has basically the self inside of it. So it's def prepare key with the argument self comma key, and inside of this method, first thing that happens is we make sure that key is of the type ECDSA signing key, or that key is the type ECDSA verifying key, and if that is the case, then we return the key. Okay, so you would pass in a key to this method from this object, which is ECA algorithm, and if the key was already of these types, you're just going to return it. If the key is a string type, and if that string type is a text type, it's going to encode the key as UTF-8. Okay, and the comments here are attempt to load key. We don't know if it's a signing key or a verifying key, so we try the verifying key first. So then it has try, and then it has key equals ECDSA verifying key dot from pem, and then it has the key, and it passes the key to it, right? And this is potentially after the key has already been encoded from string 2 bytes, right? And if this ECDSA verifying key dot from pem looks like it's a class function, right? Because this is a class, we're not instantiating this, so this is just a class function or a static, probably just a static one, but maybe it's a class. If that fails, specifically with the exception ECDSA.der.unexpected.dir, we're going to set the key to be ECDSA signing key.from pem. And basically, if the key, to come back up to this higher level if statement, if the key isn't a string type, isn't in one of the string types, we're going to raise a type error, which is expecting a PEM formatted key. And so after that, we're going to return the key. So this prepare key method, basically, if the key is ready, aka it's one of these types already, it returns it. If it's not ready, if it's not a correct form, it's just going to raise a type error. And if it is of a form that can be coerced or converted into one of these signing keys or one of these different classes, then it's going to do that and then return it. So the next method we have is one called sign, which takes self, which means it's an instance method, and it takes the argument self, comma, message, comma, key. And in Python, you could pass these as keywords or positional arguments. There's a certain type of signature where you can force the argument to be either a keyword or force it to be a positional argument. These ones can be either of them. And basically what you do is you then call this function on the key argument that you're passed, which is key.sign, and you pass that the you pass this sign function the message argument, and then the hash function, which is the hash algorithm that was defined when you initialized this class. So when you create an instance of this class, you tell it what the hash function is, and then the sig encode argument is just basically pulled from another library that we could look into if we wanted to. That's imported at the top. It's imported as ECDSA. Okay, so just to go to the last method here, this is it's called verify, takes the argument self, message, key, and sig, and what it does is it's going to try to return, it's going to try and call key.verify with the sig, the message, the hash algorithm, and then this data right here. And if that doesn't work, it's going to return false, and it's going to capture an assertion error. And obviously, if this returns an exception besides that, like say one of these other values is just incorrect, then it's going to just percolate that exception up higher, and probably it's going to fail your entire program. So that's a quick look at this first file, PyECDSA. So the next file that I'm going to be going over is pycrypto.py. and this one is inside of the algorithms directory. And so it starts off with import crypto.hash.SHA-256, followed by import crypto.hash.SHA-384, and then import crypto.hash.SHA-512, and then it has from crypto.public key import RSA, from crypto.signature import pkcs1 underscore v1 underscore 5, from jwt.algorithms import algorithm, from jwt.compat import string underscore types and text type. That completes the import on the import section of this file. And so the next section is the class declaration, the class name being RSA Algorithm. The doc string for this is performs signing and verification operations using RSA SSA-PKCS-V1-5 and the specified hash function. This class requires PyCrypto package to be installed. This is based off of the implementation in PyJWT 0.3.2. Similar to the other class, PyECDSA module, the one that's, I think it's called EC algorithm. This one has SHA-256 class variable set to crypto.hash.SHA-256, SHA-384 set to crypto.hash.SHA-384, SHA-512 set to crypto.hash.SHA-512. I should have said this earlier, but the class RSA algorithm is inheriting from a parent class called algorithm. So for the init method of this class, it takes a hash algorithm and it sets that hash algorithm inside of the instance's namespace, which is often referred to as self. The next method in this class is prepare key, very similar to the EC algorithm's prepare key. It takes a key argument and it first checks if this key is of type RSA._RSA object. Then it returns the key if that's the case, because it's already prepared. Here we have the next line, the next if statement, which is if the key is an instance of string types, then we also check if the key is an instance of a text type, and if it is, we encode the key as a UTF-8 value. So at this point in time, the key is a bytes structure. I always get, it took me a long time to get decode and encode, but basically if you have a string, you encode it, and it can be like encoded with something like ASCII, UTF-8, Latin 1, ISO 88591, or like UTF-16 or whatever, right? But if you have bytes, you have to decode those bytes in a similar way. But the bytes turn it into a string, and the decode turns it into a string, and the encode turns it into a bytes object. And both of them are obviously Python objects. So that was a little bit of a caveat or a tangent, but okay, so it gets encoded into bytes, and after that, it imports the key with the RSA module. It calls rsa.importKey, and it passes the key, which should be a bytes object at this point in time. And this is if it is a string type. If it isn't a string type, it raises a type error saying expecting a PIM- or RSA formatted key. A PIM- or RSA- formatted key. After that, it returns the key. It has another method after this called sign, which basically just passes a message and a key to the function from keys pkcs1 v1 pkcs1 underscore v1 underscore 5 dot new key, and then it chains that with dot sign self dot hash algorithm dot new, and it passes the message to this this function, and then it returns whatever it is from that, and then it has a verify message, a verify function or method after it, and this is its last one, and it takes the arguments self, message, key, and signature, and it returns pkcs1 underscore v1 underscore 5 dot new, where it passes the key to that, and then it chains this with dot verify, and it passes self dot hash algorithm dot new of message and sig to this. So my understanding basically is with a lot of this stuff, with this sort of cryptographic things, a lot of the time there's a method called sign, which is basically like taking your key and then like signing it so that people know that it's cryptographically secure and like the right person. And then there's the inverse of that, which is verifying it, right? So that's pretty much what it does. So let's go on to the next file, which is init.py. Again, this is just for Python's import system. And then we have another one, but this one is a little bit more rich. Inside of this init.py, we see the documents, we see the comment JSON Web Token implementation, minimum implementation based on this spec. And then it has a link that you could go to that would be probably useful to read. And then it defines a title for the entire project called PyJWT, a version, which is 1.7.0, an author, which is Jose Padilla, a license, which is MIT, and a copyright, which is copyright 2015-2018, Jose Padilla. Then we have the main functions, classes, Python objects that are going to be exported from this entire library that you're probably going to use as a regular developer. So this is from .apijwt import encode, decode, register algorithm, unregister algorithm, get unverified header, PyJWT, from .apijws import PyJWS, and from .exceptions import invalid token error, decode error, invalid algorithm error, invalid audience error, expired signature error, immature signature error, invalid issued at error, invalid issuer error, expired signature, invalid audience, invalid issuer, missing required claim error, invalid signature error, and PyJWT error. Moving on to the next file, which is titled underscore double underscore main double underscore, and this one has in its import section from underscore double underscore future double underscore import absolute underscore import print function, and then import arc parse, import JSON, import sys, import time, and then from dot import decode error, version, decode, encode, and then it gets into some functions that are declared in main. And I'm not sure, but this is probably if you want to run this entire module from like the command line or something. Whenever you see arc parse, that's like pretty much what's going to happen. So basically it's got a function, not in a class, so it's just a function. It's called Encode Payload. It takes args, and this args looks a lot like what you get from arc parse. So it's going to first try and encode this. So if args.key is none, it's going to raise the value error key is required when encoding, c -- help for usage. Then it has a comment build payload object to encode. It initializes a payload dictionary. And then for arg in args.payload, it splits that arg with an equals sign. And it has the key and the value here. There's a comment which is exp plus offset special case question mark. This is, I'm not sure what this is, probably related to the expiry. And so if k equals exp and v of 0 equals plus, and the length of v is greater than 1, v is set to the string of the int of the current time plus the int of v slice from 1 to the end. Yeah, this is probably so that you can interesting. So we'll just move on to the next line. Cast to integer question mark is the comment. Then it has if v is a digit, then v equals int of digit, else cast to float. Try v equals float of v, and if there's a value error, just catch the exception. And then cast to true, false, or null. Constants equal true, false, null. Okay. If v in constants, v equals constants of v. And then payload of k equals v. Okay, so that's interesting. And then after it does that for every one of the args in the args.payload thing, it's going to, after that, it's going to get a token from a function, which is encode, and it's going to pass the payload, the key, and the algorithms, which have all been pulled from the arguments, which is probably from the command line again. Then it takes this token, which must be a bytes object, as we see the decode here, and it decodes that bytes object as a UTF-8 string. Okay, and important is to figure out which encode function is this, and it is the encode function that is exported by default from this entire module. So we looked at this file a second ago, it's this encode because the dot. So I apologize if something is wrong here. I'm basically just giving my best understanding of it, but there is a very high probability that I get something wrong somewhere, and so if you do catch something like that, feel free to put that in the in the comments section, and I'll review that, and perhaps you are correct and I should update or put a caveat somewhere. Anyways, so then you have this next function called Decode Payload, which takes one argument called args, and you have try if args.token, then the token equals args.token, else if sys.standardin.is a tty, then the token is set to sys.standardin.readline.strip. Else you raise an IO error which says cannot read from standard in, terminal not a tty. Token equals token.encode UTF-8, data equals decode token, and the arguments passed to decode are token, and then key equals args.key, verify equals args.verify, and then you return json.dump string of the data. Right, okay. And basically if anything goes wrong here, well, not if anything, if a decode error is raised from one of these, from anywhere in this code, which will probably be right here, right on the decode line. So if this raises a decode error, it's going to be re-raised, but with the string, there was an error decoding the token, and then it's going to pass in the exception as the string printed after that. Then we have build Arc Parser. You see this a lot in these type of modules. It has a usage doc string. It's not a doc string, but I call these, it's like one of those really long strings that have 3 quotes. All right, so let's just read this. Encodes or decodes JSON web tokens based on input. And then it has this form, and then it has decoding examples. Basically, this is telling you a bunch of different ways you can call it from the command line. And so remember we read earlier that there's some weird stuff they might do with plus. So they've made it like where this exp, which is supposed to be like within JSON web tokens, there's this important key value that is in the JSON data, which is called exp, and it stands for expiry. And so this +10 is saying, use the current time and then add to it, and this exp is used like a just absolute time. And then in some of these other examples, it's showing how the key can be something like you can define it from the command line like secret. Then you can tell it, I guess, what mode to use. I'm probably getting some of this stuff wrong because I'm reviewing this for the first time with you guys, but it's interesting anyways. So then we get the arc parser. The arc parser.argument parser passes prog pi. Oh, prog is for program, and it's called PyJWT, and its usage is what we saw up here. So this usage is actually a string that's understood by the arc parser. And so after that, we're going to add an argument, which is -v, which is the version. Then we're going to add another argument, which is --key, which is stored inside of key, which we've seen in all the other functions so far. We see --algorithm. We haven't seen that directly, but it's stored in well, actually we have. We've seen args.algorithm. And then we see subparsers. I've never actually seen this before, where you add a subparser to the arc parser, but it accepts an argument for a title, a description, and help, which is interesting. After that, we have, oh, okay, so this is a subcommand, I guess. The encode parser is, okay, this is, you know what this reminds me of? This reminds me of Docker, if you have any experience with that, where it's like the main command line thing is Docker, but there's sub parsers that are for, like, say Docker, you know, Docker image, and then there's like a whole bunch of options after that, or Docker, you know, logs, or Docker container, or Docker stack if you have any experience with Swarm. Anyways, so yeah, it just kind of continues down here. It adds a decode parser, which accepts a token, which accepts a new line. Well, not a new line. It accepts an argument called -n, and yeah, and it returns the arc parser in the end, right? And that's what you see down here. That's what they've prepared everything for this. They get the arc parser, and then they do parse args, and they pass in sys.argv 1 to the end, a slice of it from 1 to the end, and that's because the first argument is always, I think, the name of the module itself, and you're not interested in that. And so the output of it is basically arguments.func of the arguments, right? Which is interesting. I haven't seen this before, but this is probably related to some of those sub parsers where there's like actually a func define. Yeah, we see it here, right? Right? Encode parser, set defaults, and what you're doing is you're setting the function and you're setting it to that encode function we saw earlier. So basically this is just a way of using arc parse to basically call encode or decode, which are the sub parsers in this. And then you just print the output, and if there's an exception, you just print there was an unforeseen error, and you also do print help, because it's probably because the user called the wrong thing. So that's a look at this. I'll probably never end up using this, but it was an interesting version. I mean, an interesting example of a command line program. Let's get into the algorithms.py function. Module. Starting at the import section, it imports hashlib, it imports Hmac, it imports JSON, from .compat import constant time compare and string types, from .exceptions import invalid key error, from .utils import base64 URL underscore decode, base64 URL underscore encode, dir underscore to underscore raw underscore signature. Gotta probably just ignore underscores. I'm still figuring out how I'm gonna read source code because it's kind of strange. I think sometimes I'm just gonna ignore underscores, but it's gonna make it harder for people that are just purely reading or hearing it in the audio, but I'm still figuring that out. So anyways, so from .utils import force bytes, force Unicode, from base 64 URL uint, raw to dir signature to base 64 URL uint. Then it's going to, inside of still the import, it's going to try and import from cryptography.hazmat.primitives import hashes, from cryptography.hazmat.primitives.serialization import load pem private key, load pem public key, load SSH public key, and then from cryptography.hazmat.primitives asymmetric.rsa import RSA private key, RSA public key, RSA private numbers, RSA public numbers, RSA recover prime factors, RSA CRT dump 1, RSA CRT DMQ1, RSA CRT IQMP, and then from cryptography.hazmat.primitives.asymmetric.ec import elliptic curve private key, elliptic curve public key, and from cryptography.hazmat.primitives.asymmetric import ec padding, ec and padding, and from cryptography.hazmat.backends import default backend, and from cryptography.exceptions import invalid signature. After this, it sets a a module level flag, which has crypto to true, and if it can't import any of those things, it says has crypto to false. And then we have a module level variable, which is a set with the values in it. It's called requires cryptography, and its values are RS-256, RS-384, RS-512, ES-256, ES-384, ES-521, ES-512, PS-256, PS-384, and PS-512. And then there is a function which is called getDefaultAlgorithms. This returns the algorithms that are implemented by the library. And inside of here it has a dictionary called default algorithms with the key none equal to the class none algorithm, which with the key HS256 equal to the Hmac algorithm, passed in the Hmac algorithm constant, I would assume, SHA-256. Then it has HS384 with the Hmac algorithm, class passed SHA-384, and the HS512 with the value Hmac algorithm, Hmac algorithm.SHA-512. It uses the flag we talked about earlier, if has crypto, and if it has crypto, it's going to add a bunch of other algorithms to it, which are, ones we already read, RS-256 to like 512, ES of a bunch of those, and then PS of a bunch of those. The important thing here, I guess, is to see that RS is going to be mapped to the RSA algorithm class. ES is going to be mapped to the EC algorithm class, which we've gone over these things before earlier in the video. PS is going to go to the RSA PSS algorithm class. And so we've got what looks like 4 different algorithms, each with around 3 to 4 different SHA sizes, or like, I don't know, yeah, I think, yeah. And those are Hmac, RSA, EC, and RSA PSS. Okay, let's move on. We've been interested in this class. This is the base object for all of the other algorithms we've seen. This algorithm class is has the comment, the interface for an algorithm used to sign and verify tokens. Okay, it has a class called prepareKey, which performs necessary validation and conversions on the key and returns the key value in the proper format for sign and verify. It raises a not implemented error. And then it has a sign method, which returns a digital signature for the specified message using the specified key value. It's not implemented. The verify method verifies that the specified digital signature is valid for the specified message and key values. Okay, and then it has a static method, which is toJWK, which serializes a given RSA key into a JWK. And then it has from JWK, which has the comment deserializes a given RSA key from JWK back into a public key or private key object. Okay, and all of those are not implemented because this is basically like an abstract class. He could have probably used the abc.abstract function, or I think that's what it's called, wrapper or decorator for all of these, but he decided to just do it that way. Okay, so here we see the none algorithm class. In its prepare key, it checks if the key equals an empty string, and it sets it to none, and then it checks if the key is not none, and it basically raises an exception if the key is not none, saying when alg equals none, key value must be none. Then it returns the key. When it signs, it basically just returns a empty byte string, and when it's verified, it returns false. Then we have the Hmac algorithm we saw earlier. This performs signed-in verification operations using Hmac and the specified hash function. So these are the different hash functions. We initialize it by passing it the hash algorithm, and then we prepare the key, and when we get the key, we pass it to a function that forces the key to be bytes. This is actually reminiscent of what we saw earlier, where it's like if it is text, it's then encoded into bytes, right? So then it has a value which is a list called invalid strings, and each one of these has a byte string which is a begin public key, a byte string which is begin certificate, a byte string which is begin RSA public key, and a byte string which says SSH-RSA. And then it has a line where it says if any, and then it's past the list. Man, how am I going to read? Am I going to read this? I'm going to try and convert this to English, or am I going to read this list comprehension? Just maybe I'm going to do it like that. So I'm going to experiment with this for a second. So basically this list, it's going to take all the invalid strings. It's going to take each string value, and it's going to check if the string value is in the key for string value in invalid strings. Okay, so you pass this method the key, and then you have all these strings that we looked at before, and if any of those strings are actually anywhere in the key, it's going to basically raise this exception, which is an invalid key error, and it's going to tell you the specified key is an asymmetric key or X509 certificate and should not be used as an Hmac secret. Oh, okay, yeah, this makes sense. So this is trying to capture a client error where they misunderstand how you actually make an Hmac, how you actually encrypt with the Hmac algorithm, and you're not supposed to use an X509 certificate. You're supposed to use something else. So I'm going to still be, as I read through more of this source code in real time with people, I'm going to figure out the best or some of the better ways to read some of this stuff. All right, so moving on though. Then we have a static method, which is called toJWK, which takes a key object and it returns basically json.dump string or json.dumps, and it passes the key k with force Unicode base 64 URL encode force bytes key object. So that's if you read it from left to right, but basically what it, I'm going to try it a different way. First you take a key object, then you turn it into bytes, then you base 64 URL encode it, then you force that to be Unicode, and that's the value for this k string. For this key of the value k. Then the next key is called KTY, and that's just set to oct. I'm not sure what that is for. For those, dump string is basically going to take a dictionary and turn it into a JSON string, right? All right, so whereas JSON.loads is going to take a string and it's going to turn it into a Python dictionary. Next, we have another static method, which is from JWK, and it's going to be passed at JWK. So first thing it does is it's going to do JSON.loadString. So we know that JWK is basically just a UTF-8 string, and this is a dictionary, and then it's going to get the KTY value from this dictionary and check that it does not equal OCT. Okay, and if it doesn't, it's going to raise an invalid key error which says not an Hmac key. Then it's going to base 64 URL decode basically the value of k inside of the JW the dictionary. Then it has a method called sign, which is going to basically use the Hmac library new method, and it's going to pass the key, the message, and the hash algorithm, and then it's going to return a digest. I've kind of called this type of thing before a lot of the time, but I still don't have that much experience with it. And then you have the verify sign side of things, which is basically just going to take the signature, and then it's going to actually use the sign method. So it's going to take the signature and compare it to the message and key and make sure that they're, I guess, the same. It's using a function called constant time compare. All right, so then we have this if has crypto line, which is like going to be done at the module level, right? So basically it's going to create this class, which is RSA algorithm, if those cryptography.hazmat dependencies exist. And this RSA algorithm class inherits from the algorithm parent, and it basically has all of the SHA functions in it. I think they've all been hashes.SHA-256. Nope. Some of them are from a different thing. I wonder what that is. So far in all of the classes that are algorithms, we've seen hashlib.SHA-256, but this time we see hashes.SHA-256. I'm not quite sure. They might literally be the same. They might not. You would think that they would be different in some way if they're going to go through the effort of basically using a different one. Not sure how they're different though. That's interesting to notice. So the init is the same as all of them. It passes a hash algorithm. The prepare key is similar too. It checks for the type, and if the type's already RSA private key or public key, it's good. And if it's a string, it's going to basically turn it into bytes, and then it's going to try to basically, if the key starts with SSH RSA, it's going to try and load an SSH public key from it using a backend, which is like, a hook for this library. And then it's going to pass the key to it. Otherwise, it's going to try and load a pim.private key. So if it's not SSH RSA, it's going to use it's going to try and load a pim private key, and it's going to pass it the key and use a backend again, right? The other place I've seen this is like, stuff like tk-enter and matplotlib, where there's like entire different backends that do a large portion of like some of the code in the library. So just interesting thing there. So if one of these returns a value exception, then we're gonna set the key to load a pim public key, and in the same form, and basically similar to the other prepare key functions or methods we've seen, if it's not a string type, we raise a type error which says expecting a pim formatted key. Then we return the key. This is the only one of the algorithms we've seen so far that has a 2JWK, I think. This function is also static, as it has to be, which, if you're not familiar, that just means it doesn't have a instance namespace, often referred to as self, or a class namespace, which is often referred to as CLS, or class. All right, so the first thing it does is basically look for private numbers inside of the private numbers key inside of the key object, and if it doesn't find that, it's going to return that. It's going to return, and that's going to give it numbers, this value numbers, and then it's going to build an object from it, and that object is going to have a key value of key ty of RSA, a key value of key ops, which is a list with the value sign in it, Oh yeah, okay, this makes sense. Ops is probably like the operations that you need to do on it. And this is just a list of those methods that are going to be available. Then it has a key of n, and then we're going to start, since this is a nested wrapping thing, we're going to go inside out because that seems to make more sense. So it's going to use the numbers.publicNumbers.n value, and it's going to convert that to base64 URL, which is also of a type uint. Okay, so if you're not familiar with base64, the whole point of it is that it uses like characters from like A to, I think, from like lowercase. It basically uses, I think, basically like 64 different characters to encode arbitrary binary. That might be, I may have said that wrong, and it was created because when you send stuff through the URL, you can't send arbitrary binary. It's not valid data. So what you can send, though, are base64 things. Pretty much like base64 is a subset of ASCII, right? ASCII has like around like 128 different values because it's a 7-bit encoded string character like type language thing. That was probably not said that well, but basically it's got like a bunch of values. This has a subset of those values, and it uses that subset to be basically like opaque binary data. And that's where you get to this part, which is uint. So it's being converted to binary data, but it's being converted to binary data that is going to be of the type uint, which is a C type, but you see it in other places a lot of the time. And so that's my best guess of this. Like I said, I'm reading through this for the first time. So it's going to base64 URL encode it as the data type uint, and then it's going to force that to be Unicode. And it's going to do that for all of these different keys. I'm just going to move past this since it's basically the same for all of those. And that is all, again, if it has private numbers in it. If it doesn't have private numbers in it, it's going to check if it has verify in it. Verify in the key object. And if it has verify, it's going to basically pull public numbers from the object as the numbers, and it's going to do the same thing. It's going to build an object with different keys and values that are basically using those values. And if one of those cases isn't correct, it's going to raise an invalid key error. And after all that's done, it's going to take that dictionary it created, and it's going to dump it as a JSON string. All right, and so next we have another static method, which is from JWK. It's going to try and load the JSON from here, and if that doesn't work, it's going to tell you that the key is not valid JSON. Then it's going to look for this key, and if it's not set to RSA, it's going to tell you, it's going to raise an exception saying this is not an RSA key, invalid key error. Then it's going to check if D is in the object, E is in the object, and N is in the object. And if those are the case, then it's going to immediately check if OTH is in the object. And if it is, it's going to raise an invalid key error saying unsupported RSA private key. And then it's going to say greater than 2 primes are not supported. Okay, and then it's going to create a list which is called other props, which has a bunch of different letters in it which stand for keys, which are keys. And then it's going to do props found, and it's going to do basically okay, so the best way to read list comprehensions is sort of in backwards order again. So for each prop in the other props list that we just saw, we're going to check that that prop is in the object. And if it is, we're going to set that in another list called props found. Then we're going to check that basically every single, okay, that was a little bit incorrect. Let me read this again. For each prop in the other props, we're going to create a Boolean, which is, it's going to have a value of true or false, and it's going to be whether this prop is in the object. Then we're going to check every one of those Booleans in that list, and basically if any of those aren't in it, it's going to have a value of false, right? And so what we get down here is if all of the props were found and all of the props were found. That's interesting. Or I mean, sorry, if I did this. I did this wrong. I read this as all instead of any. So basically, the logic is inverted. It's like if any of the props are true, then this will be true, right? But then this is the other one, which is if any of them are false, this is going to be false. So this if statement is basically like if one of the keys is in the object and all of the keys aren't in the object, then raise an invalid key error where it says RSA key must include all parameters if any are present besides D. And that makes sense. All right, then after that, you get the public numbers from this class RSA public numbers. And what you do is you take it from the object. You've got these different keys, and you do this whole convert it to base 64. And after that, you have your public numbers. You've checked that everything is valid with the properties in the object. You've checked that the object can itself be converted to JSON. You've checked that specific things are in it and that other thing. Basically, you've checked a lot of different stuff to make sure that it's going to work out. And then you've extracted this public numbers, or you've created this public numbers data from the object itself. Then if any of the props were found in the object, you're going to create another object called numbers, which is RSA private numbers. So you have your public numbers, now you're going to create your private numbers, and that's going to use all of that data you got from that object earlier, just converted to base 64, and it's going to put it in basically the same, actually not the same keys. These are keys that are more for Python's processing, whereas these are keys that are literally going to be in the JSON itself. Okay, so that's if any of the props are there. And if there aren't any of the props, then we're going to basically just get this value from D, and then we're going to call this function RSA recover prime factors, and we're going to pass it the .n value from public numbers, the D value that we just calculated, and the .e value from public numbers, and then we're going to create this same value from RSA private numbers. So basically, we're going to create private numbers, we're going to create public numbers, and then we're going to return a private key using the default backend from that class, that private numbers class that we just created, basically. And that's all going to happen if those keys are inside of the object. If those keys aren't in the object, but instead N and E are the only ones in the object, we're going to create a public key. And if we receive anything that's not like that, we're going to raise an invalid key error, saying it's not a public or private key. Okay, and then it's got a sign method, which is going to pass the message and then something called padding.pkcs1v15, and then our hash algorithm, which in this case is a callable to this key.sign method, and it's going to return that. And then to verify it, or the verify method, is got the same signature, and it's going to be running a very similar thing, and it basically just returns true and false. Then we have what looks like the last class in this section. No, we have two more classes. This class is called EC Algorithm. What's interesting is, does this not exist here? I'm checking again. We've already seen an EC algorithm, and now we're seeing another EC algorithm, and we've already seen an RSS, right? An RSA algorithm. We saw that. And we saw, okay, so we've already defined an RSA algorithm and an EC algorithm. And I think that this was another RSA algorithm. Right, okay. And this is like the big caveat, right? If has crypto, basically this is going to rely on cryptography.hazmat, primitives, probably something like that. Whereas these ones, those other libraries we looked at earlier, they are going to be created if that doesn't exist. And they're going to use hashlib, which is like an older version that can still accomplish the same thing or a similar thing. Okay, so here's another EC algorithm. It's almost exactly the same as the the one that we looked at before. The only notable difference is that this uses force bytes instead of that code we saw before. And yeah, probably it's got a sign method, it's got a verify method. I think it's probably almost exactly the same. See, this is what the force bytes looks like. It's basically that, or it's like one of these things. Oh. Okay, so it looks a little bit different. Right. Okay, so anyways, I think that's a close enough look. There's a lot of repetition here that has differences, but they're not that readily apparent from just this code. They're going to be more so about the way the cryptography itself actually works, the requirements for it. Probably you're going to find better information about that in something more like an RFC than here. So yeah. Okay, so on to this next file, which is titled API-_JWS.py. Let's just jump into it from the top, starting with the import section. So they import bin ASCII, import JSON, import warnings. They create a try block, and from typing, import callable dictionary list optional union, and then they close that with except import error pass. Then they from .algorithms import algorithms, get default algorithms, has crypto and requires cryptography. From .compat they import mapping, binary types, string types, and text type. And then from .exceptions they import decode error, invalid algorithm error, invalid signature error, and invalid token error. And from .utils they import base64 URL decode, base64 URL encode, force bytes, and merge dictionary. Okay, so let's look at the first class in this module. It's called PyJWS. Its parent, it inherits from object. You don't have to do this anymore, but this is kind of a symptom. I don't know if there's really a difference between doing this and not doing it, but I think I read somewhere that it's not necessary really anymore. So you see it in some older Python code that hasn't been updated, although I think it's really just not that important. So class PyJWS, it has a class, it has a variable in the class namespace called header type, which is set to JWT. And then let's look at the initialization method. It has self, algorithms defaulting to none, options defaulting to none. And both of those are positional or keyword arguments. Then it sets algorithms to this function that was imported called get default algorithms. So those are the defaults. And then it sets valid algorithms. Let's see. So let's break this down. So it converts the algorithms to a set if algorithms is not none. Otherwise, it converts the self.algorithms to a set. Okay. Okay, then he has a comment here, remove algorithms that aren't on the whitelist. Yeah, this is pretty straightforward. And then for key in self.algorithms.key, if key not in self.valid algorithms, then delete it from self.algorithms. And if not options, set options to a empty dictionary, and then then basically set options to merge the dictionary with something called self.getDefaultOptions, and then the options dictionary we already had. So this initialization is basically just setting up some options data and some algorithms data. Then we have a static method called getDefaultOptions, and all it returns is a dictionary with a single key called verifySignature with a value of true. Then we have a method called Register Algorithm. This is an instance method. It has arguments algorithm ID and algorithm object, and its description is registers a new algorithm for use when creating and verifying tokens. It checks if the algorithm ID is in the algorithms that the instance was initialized with. If it's not, it raises a value error. Actually, if it is in it, it raises a value error that says algorithm already has a handler. And then it checks if the algorithm object is of type algorithm. And if it isn't of type of algorithm, it raises a type error and it says object is not of type algorithm. Then it takes the algorithm ID and it basically updates the algorithms dictionary with the key algorithm ID equals the algorithm object. And then it adds it to the valid algorithms set. Okay, the next method, instance method, is Unregister Algorithm. It's going to probably do the inverse of the register algorithm operation we just saw. Its description is unregisters an algorithm for use when creating and verifying tokens, throws key error if algorithm is not registered. It checks if algorithm ID is not in self.algorithms. Then it's going to raise a key error saying the specified algorithm could not be removed because it was not registered. Makes complete sense. And if after that it just deletes the key algorithm ID in algorithms, and then it removes the key algorithm ID from the set valid algorithms. Then we have a get algorithms method. It just wraps list around the set self.valid algorithms. Its description is returns a list of supported values for the alg parameter. And then we have an instance method called Encode. Its arguments are self, payload, key, algorithm defaulting to HS256, headers defaulting to none, JSON encoder defaulting to none. And all of these are positional or keyword arguments. And so within this method, it first creates an empty list called segments, checks if algorithm is none, and if it is, it sets it to a string that's lowercase none. And then it checks if the algorithm is not in the valid algorithms, and then it just passes. So not sure what this is, but it doesn't really do anything. Then he creates a header data type or a header data structure, which is just a dictionary with two keys, TYP or type, and then ALG or alg. They have the header type and the algorithm that it was passed, okay, which could be none, I guess. And the header type is always for this JWS, I believe. So then we check if the headers are not none, which they are never none. Well, no, the headers were passed in. This header was initialized there. So if they're none, then it's going to validate the headers. And if they're valid, I assume that this is going to raise an exception. And basically, if they're valid, it's going to update the header dictionary with the additional headers that were passed in from the arguments. And then it's going to create the JSON header by basically passing the header, basically JSON encoding the header. And this is an interesting, I've never done this with JSON dumps myself. I always just use the default where you just pass in a UTF-8 encoded string that is then, or you pass in a dictionary and then it'll give you a UTF-8 encoded string. But what you can actually do as well, which is interesting, is define what separators you want to use and define what class of JSON encoder you want to use. So I guess I just use the defaults for this whenever I use that. And then what you're going to do is take that UTF-8 encoded string and you're going to force it into bytes, and that's going to be a prepared JSON header. But even then, what we're going to have to do is prepare it to be sent over the network, which is going to base64 URL encode it. Technically, it could be sent just as bytes over the network, but the reason you have to use base64 URL encode is to make it safe in case it ends up in a URL. And then after you have that form, you're going to append it to the segments list. And then after that, you're going to do the same thing with the payload. You're going to base64 URL encode the payload, which must already be a bytes object. And then you're going to get the signing input, which is going to join the segments together with a period. I remember this. I read the JWT RFC, and this is sort of like what happens. To sign it, you take this base64 URL string thing, and then you take the next one. For the JSON header, you take it, then for the payload, you take it, and then you join them together with a period. This is a byte literal, and I haven't mentioned this before, but byte literals were kind of, sorry, it's not a byte literal. A binary literal is not what it is. It's a byte string. And as you can see, even now, I called it the wrong thing. Byte strings were sort of confusing to me for the longest time because I didn't know exactly what it is, but basically the way it works is that this is just a ASCII encoded. You can basically put any ASCII inside of this byte string, and it will automatically be converted to like its binary form when you use it. But you can't put anything that's not that's larger than a single byte. So you can't just use UTF-8 strings. If you want to do that, you just have to use a regular string and then encode it, right? And that's obviously different than a binary literal, which I'll have to go into some of that stuff. Maybe I'll make a video about that. But anyways, to move on, you join them with this byte string period. Then you're going to basically try to, I got to figure out the best way to say try blocks without it just being verbatim. Maybe it's just best for it to be verbatim. But so you start a try block. You get the algorithm object by using the algorithm string as the key for the self.algorithms dictionary. Then you get the key from the algorithm object by preparing the key with the key that was provided. And this is kind of like your secret. It can be an arbitrary password. And then you finally obtain the signature. And you get that by calling the sign method. And you get that by using the signing input, which is both of those, the payload and the JSON header combined together, and then also the key. And when you combine all this together, it creates the signature. And then what you're going to see is the signature is going to be base64 URL encoded down here and attached to the segments as well. And then you're going to join it with a period as well. And you're going to end up with the JSON header, period, payload, period, and then signature. And that's what makes up a JWT when you encode it to be sent over the internet somewhere else. Of course, what I didn't mention is that there can be a key error. And I've actually gotten this before, I think. But the first part of the key error is if they don't have the cryptographic libraries, which this is the flag has crypto, but what it really stands for is if cryptography.hazmat is installed, like if you can import that correctly. So if you can't import cryptography.hazmat and the algorithm is in one that requires that library, then raise a not implemented error and print out the string algorithm could not be found. Do you have cryptography installed? And if there's a key error that and has crypto is installed, or basically other than that condition, then you do raise not implemented error, algorithm not supported. So actually I haven't ever gotten this. I haven't even really, I have specified when I've made JWTs, I've specified the algorithm. I always used HS256, I believe. That's sort of like the first one I saw. So anyways, let's look at the inverse, decoding. This is very important to do when you're on, like say you're writing a Flask web server and you're going to use JWT tokens to authenticate people. You're going to have to both encode it for when they log in. They give you their credentials, you derive the JWT, you send it back to them, and then every other request they're going to send you the JWT, like with all of the stuff that we talked about before. The header, the payload, the signature, right? And so when you decode it, you're going to have the JWT, which is here. You're going to have your key, which is the secret that you defined. You're going to have verify defaulting to true, algorithms equals none, options equals none, and then they're basically going to catch all the rest of the KW args in that argument. And so the first thing you do is get the merged options in the way that we saw before with the merge dictionary method. You see this type of stuff a lot. Almost every library author has their own way of doing that. Then you're going to check if verify signature is init. And if you remember, this was the one thing that always defaults to true. And then, because that's like the whole point of this function, right? So if verify signature is true, but there isn't an algorithms list, then they're going to send a warning. And they're going to be like, it is strongly recommended that you pass in a value for algorithms argument when calling decode. This argument will be mandatory in a future version. Okay, so you need to make sure you have both of those. Then what you're going to do is you're going to load the JWT, which this is going to be a cool method to look at. Basically, it's just going to unpack everything, right? I mean, you could probably even just see this being a split string on period, right? So you're going to have your payload, the signing input, the header, and the signature. And then we check again, if not verify, then you're going to they're going to print a warning, which is the verify parameter is deprecated. Please use verify signature instead. This is a good example of like if you use keywords. I read another PEP that was, I forget what it was, maybe like 570, but it was talking about how you should have, how Python needs to have positional arguments only, positional only arguments. And this is an example of how a library in an earlier version defines a keyword that if it gets rid of it is going to kind of break everything. And if it was a positional argument, it would work better. Anyways, that's sort of a tangent. So the last thing you basically do in this method is if you're supposed to verify the signature, which should always be the default, then you're going to call the verify signature method on it and basically pass in the payload, signing input, header, signature, key, and algorithms. And what I'm assuming is that basically if you verify the signature, this isn't going to be like, this is itself going to raise an exception. And so if it is verified, you're just going to return the payload afterwards. Okay, so the next method is get unverified header. The description is returns back JWT header parameters as a dictionary. Note the signature is not verified, so the header parameters should not be fully trusted until the signature verification is complete. Okay, so it uses this thing we saw before, loads, and it takes the second element of it, and that's the headers, and that validates the headers, then it returns the headers. Here's the load function that we saw before. First thing it does is check if the JWT is a text type. And if it is a text type, then it turns it into a byte type by encoding it with UTF-8. Next, it checks that JWT is not a subclass, so if the JWT type is not a subclass of a binary type, then raise a decode error which says invalid token type, token must be binary type. Okay, that should be the case if it's, if it was a text type, it'll be encoded first, turned into a bytes object. So then we're gonna open up a try block. We're gonna do, exactly how I said, we're gonna split the JWT token, which is a byte string. We're going to split it on the byte string period, and we're going to take the first element. And from the first, I think that's what that one means. I'm not exactly sure. But basically, this is going to give you the signing input and then the crypto segment. Okay. And then we're going to split on the period again on the signing input itself. And we're going to get the header segment and the payload segment. And this can raise a decode error, which will basically tell the user not enough segments in case it's an invalid JWT. So then what we're going to do is we're going to decode the base64 URL header segment, and we're going to get the header data from it. And this could have a exception, which basically they're interpreting as invalid header padding. That's interesting. The next thing you're going to try and do is load the header. Okay, so this is like kind of shows the whole process of marshalling sometimes and demarshalling. Basically, it's also called serialization sometimes, but basically first you break up the entire chunk of data with the period delimiter. Then you base64 URL decode it. Then you're going to UTF-8 decode the bytes themselves. Then you're going to JSON load the bytes. And if all of that works, you're going to have a correct header. And then you're going to do the same thing for the payload, basically. You know, base64 URL decode it. Then you're going to base64 URL decode the signature. And then you're going to return all four of those things. And so, all right, so now we're going to look at the verify signature method. All right, this thing is going to get the alg data outside of the header key alg. Then it's going to check if algorithms is not none and alg is not in algorithms, raise invalid algorithm error. Then it's going to try to basically get the algorithm object from the dictionary with algorithms in it. It's going to prepare the key that was provided, and it's going to pass the key, the signing input, and the signature to the algorithm object to verify it. And if this returns false, then it's going to raise an invalid signature error. And otherwise, it's going to say it means you didn't use basically a valid algorithm, probably. Yeah, a key error. This key error is referring to when you look it up in the algorithms dictionary. It could have a key error. Then there's this method called validate headers. And this is just going to check if KID is in the headers. And it's going to validate the KID with the data, with the value from the headers KID key. And then it's going to have this validate KID method. And it's going to basically check if the KID is in the string types or that it's not in these string types. And it's going to raise an invalid token error saying the key ID header parameter must be a string. All right, and then we have at the bottom of this entire module some module level variables being declared. So they're being put into this namespace for API JWS. This one's a JWS global object, which is just an alias to the PyJWS class we just looked at. I guess it's actually literally an instance of the class. And then we have the encode method from that instance, the decode method from that instance, the register algorithm from that class or from that instance, unregister algorithm, and get unverified header. All right, let's move on to the next module here, API underscore JWT. So we did JWS, now we're doing JWT. All right, so let's start with the import section. Import JSON, import warnings, from calendar, import time GM, from datetime, import datetime and time delta. Then try to import from typing, callable, dictionary, list, optional, and union. Pass on any import error. From .API.JWS, import the PyJWS class. From .algorithms, import algorithm and get default algorithms. From .compat, import iterable, mapping, and string types. From .exceptions, import a decode error, expired signature error, immature signature error, invalid audience error, invalid issued at error, invalid issuer error, missing required claim error.
And then from .utils, import the merge dictionary function. So first thing we see is class PyJWT extends PyJWS. So everything we just saw is going to be applicable to this class, except it's probably going to override a bunch of things. So its header type is JWT instead of JWS. That's a class variable. It declares a static method, which was declared before, called getDefaultOptions. And this returns a dictionary with verify signature true, verify exp true, verify nbf true, verify iat true, verify aud true, verify iss true, require exp false, require iat false, require nbf false, which is interesting. If you read the JSON Web Token or JWT RFC, it goes into detail about what all of these things are. And I can't remember exactly what these things are. But I mean, I know vaguely, like, the EXP is basically an integer, which is a timestamp. But anyways, so let's look at the encode method that it's going to define. It takes payload key algorithm, defaults to HS256. This is what I use. Headers equal none, JSON encoder equals none. And then basically we're going to check that the payload is a mapping type. And if it's not, we're going to throw a type error. We're then going to check that the time claim is basically either the value EXP, IAT, or MBF. There's a comment that says convert datetime to an int date value in known time format claims. And so what we're going to do is from the payload, we're going to get the time claim, whatever it is, and we're going to check if it's an instance of datetime. And if it is an instance of datetime, we're going to set the time claim, which is just one of those strings that I talked about before, to basically time GM. Okay, let me do it this way. We're going to take the date time, call UTS time tuple on it, and then pass that value to time GM. I'm not that familiar with these different functions, but that's what it's doing verbatim. So then to get the JSON payload, we're going to take the payload. We're going to basically, the payload is a dictionary. We're going to turn it into a JSON string. Then we're going to encode it as UTF-8 to make it a byte string. And then that's going to be put in the JSON payload reference. Then we're going to pass the JSON payload reference with the key, the algorithm, headers, and JSON encoder to the method that was declared in the PyJWT class, basically the parent method. So all that really happens here is we do a little bit more checking of stuff. We convert some of the date times, and we prepare the JSON payload, and then we just pass it to this encode method itself. And if you remember, in this encode method, it checks if the JSON payload is a string itself, but it also just accepts a bytes object. So it all works out. Basically then, we have the method decode, which has JWT, a key, a verify, and algorithms and options, KW args. You know, it does what looks very similar to before. Yeah, it loads the payload. It calls the self.load method with the JWT to get the payload. It ignores everything else. Right. And then it just passes everything to the parent to decode method. Right. Why does it even get the payload out? Kind of curious about that. After it passes it to the decode method above, it has decoded this value called decoded. Then it tries to basically load JSON from the decoded value, which is being turned into a UTF-8 Python string object, and then into basically a Python dictionary. And there can be a value error, I suppose, that's caught if there's an invalid payload string. It's probably from the UTF-8 or the JSON loading. And then the payload, if the payload is not an instance of a mapping, it throws another error. And then basically it's going to validate the claims. This is where the payload is finally used. So, that's interesting. I'm not sure why this payload is even extracted up here, because it's not used and then it's just reset down here, right? That's interesting. So anyways, let's move on to the validate claims method. This takes a payload argument, options argument, audience argument, issuer argument, leeway argument, and then KW args. This is going to be interesting because you're going to get a little bit more into what the JWT RFC was talking about with these different keys, which are also called claims. If verify expiration is in KW args, set options verify exp to KW args.get verify expiration, or just default to true. Warnings.warn the verify expiration parameter is deprecated. Please use verify exp and options instead. Okay, then we check if leeway is a time delta type, and if it is, then you convert it to seconds. Then we check that the audience is in the types. Basically, we check that the audience is either an iterable, a none type, or a string type. And then if that's not true, we raise a type error where we say audience must be string, iterable, or none. Then we have basically self.validate required claims with the payload and options. So, okay. And then we get now from this thing that we saw before, datetime.utc now.utc time tuple, and we pass it to .time gm, and that is this now value. And if IAT is in the payload and options.get verify IAT, then self.validate IAT with payload, now, and leeway. Okay. If NBF in payload and options.get verify NBF, self.validate NBF payload now leeway. If EXP in payload and options.get verify EXP, self.validate EXP payload now leeway. Okay, if options.get verify ISS, self.validate ISS with the payload and the issuer. And if options.get verify AUD or audience, self.validate audience with the payload and the audience. Okay. So basically, it's just validating what it's supposed to validate. Let's get into the next method. Validate required claims. Pass payload and options. If options.get require exp and payload.get exp is none, raise missing required claim error exp. Okay. If options.get required IAT and payload.get IAT is none. Basically, this is just checking to see if those values exist and raising a missing required claim error if they don't. The next one, which is validate IAT, is basically just trying to make, it's just making sure the IAT is an int. It's just, the next one is just making sure that the MBF is an int. And then it's checking that the MBF is actually after the time plus the leeway. And the validate EXP is the same thing. Make sure it's an int, but make sure it's the reverse. Make sure that it's before now minus the leeway. And the audience is basically just, you just check to see that it's there. And if it is there, if it's a string type, you wrap it in a list you put it in a list. If it is a list, then say that's interesting. I'm not sure I follow this. Okay. Okay, so if audience claims, okay, so audience claims is the value payload of the key AUD. If it's a string, make it a list with the string in it. If it's a list, raise an invalid audience error, which is an invalid claim format and token. And if basically for every, I guess every audience member in the audience claim, or every basically string, make sure that it is a string. And if any of those aren't a string, then raise this. What's confusing to me is that it looks like if it is a string type, then you convert it to a list, which means that immediately afterwards, oh, I guess this is if it's not a list. My bad. Basically, the audience has to be a list of strings. Or the audience claims has to be a list of strings, but it looks like the audience is exactly the same. So it just checks that. That's it. The issuer, we just check if it's in the payload, and we just check that the ISS is the same as the issuer. Okay, I say this in a lot of my videos because things are just, you know, I don't know, code is just complicated, and RFCs, computer science is just hard, man. And so I get confused sometimes, especially when I'm reading a lot during the day. It's like at some points, I feel like my brain just stops working. But this is pretty kind of confusing to me, but I just don't know what the point of some of this stuff is. Like if you really have to have it and how it helps. But anyways, all of this stuff is then packed into the JWT global object. And this API JWT does the same thing that we saw before. We just basically take those class instance methods and we put them in the module itself. Why? I'm not sure. It just seems like an arbitrary decision for the library author to do, to basically just be like, I want these to be there so that you can just use them directly from the library. If I come up here, I look at init. You see, init just imports from API JWT and API JWS. It doesn't even import from API JWS any of those encodes and stuff that it made available technically. And so really all you're doing is, you know, I guess it provides the class if you want to actually use the class, but most of the time it just understands that you're just going to call the library like jwt.encode. Anyways, let's move on. We're getting close to the end of this entire library. Okay, so we've got a description. This is a compatibility library. We see this stuff in almost all libraries. It imports the Hmac, it imports struct, it imports sys. It checks Py3 by looking at the system.versioninfo of 0 and that it equals 3. Stores it as a true/false value. If it is Python 3, then it sets the text type to be string. Otherwise, it sets the binary type, or no, it sets the text type to string and the binary type to bytes. But if it is not Python 3, aka it's Python 2, the text type is Unicode, and the binary type is a string type. So then it sets the string types to either binary or text. So you can see here in his library, he's indifferent about it being binary and text. We see that over and over again. And that's why you can use a binary string and a Unicode or UTF-8 string. That's like what the default Python strings are. Kind of like with indifference. And the library will just work around it. Then he's going to try and import from collections.abc iterable and mapping, and if that doesn't work, he's going to import instead from collections iterable and mapping. This is again just like a Python version thing. Then he's going to try and get constant time compare from hmac.compare digest. And if that attribute doesn't exist in hmac, the hmac library, he's just going to write the function himself here. So we actually know what it does because we have it here. We have the equivalent one. The equivalent one compares the two values' lengths. They have to be the same. If they're not, it's false. Then it basically zips both of the values together, which are probably strings. And it checks that each one of those... Oh, okay. So the result is a 0. And then he's doing some bitwise logic here. He's ORing this result with the XOR of the ordinal value of X and Y. This is an interesting way of basically like mashing the bytes together of this stuff. And interesting. And if return result equals 0. So basically, if the binary is exactly the same, it's going to be, I'm guessing here, I'm not really an expert at this stuff, but I'm guessing that the binary will be a value of 1 and the constant time compare will return false. Okay, we can just read the description. Returns true if two strings are equal, false otherwise. So, oh, okay. This is probably what happens here. Because, okay, so if you have 0 and you bitwise OR it with like, you know, any values of 1s are going to be copied there. So, therefore, you know, any value that's not 0 here is going to not be equal here, which means it's going to be false. So then it means that when you XOR the two things, yeah, this makes sense. I reviewed this so long ago in, you know, I got a bachelor's in computer science, and, you know, but this is a good review for myself. Basically, bitwise XOR, the way it works is if you've got 1, 1, 1, if you've got a 1 over here and you've got a 1 over here and you put them together, that's a 0. And so when you have the result being 0, when you OR a 0 with a 0, it's just a 0. And so if the binary between the first string and the second string are literally the exact same, all of the XOR will be, you know, will return a 0. And that means that when you OR equals that with the value of 0, you know, it's harder to explain this, or it's just much more detailed to explain it. But in a nutshell, if they're equal, it returns true. And if they aren't, it returns false. The question is, why wouldn't you just use a string to like compare that? I don't know. I guess this is faster. Time taken is independent of the number of characters that match. Okay. Anyways, sorry if that was confusing. And sorry if it's incorrect, but let's move on. Okay, so then we check here. I've actually used this function before with the integer type in Python. You can actually call a .2bytes method in it. And what they're saying here is if that doesn't exist, let's create this function. And otherwise, let's just use the function. So if 2 bytes is in int, then define this function bytes from int, which takes a val, and remaining equals val, byte length equals 0, while remaining doesn't equal 0, remaining equals remaining, bitwise shifted 8, and the byte length is plus equaled 1. And then return val.2bytes, because val is already an int, and we pass in the byte length. We pass in the network, the byte order, which is always going to be network probably, which is big. And then we pass in whether it's an unsigned or signed integer. This is honestly where Python just looks like C code because it's using so much of what happens in C code itself. It still doesn't really look like it, I guess, but it's using a whole lot of the same concepts. Okay, and that's if the int object has the 2bytes method. Otherwise, we're gonna do another method called bytes from ints. From int, we create a buffer that's a list. We create a while value, and then value and remainer equals div mod val 256. That makes sense. And then we append the remainer to the buff, to the buffer, and then we reverse it. This is probably doing big Indian right there. And then we pack it with this struct library. The kind of interesting thing that I can speak to is, what is div mod val 256 equivalent to? Basically getting a byte from an integer. And you just keep doing that, and you'll get each byte one after another. Then you reverse it, and then you pack it. And again, I apologize for any errors. I'm doing this in real time without preparing and double checking. That's just, and just to speak to that, to ramble a little bit more on that, the reason I'm doing it this way, and I'm like, in my opinion, reading through source code and reading through all of this documentation, which is ultimately my goal, is a costly endeavor. If I make sure I don't make any errors while doing it for my audience, that just makes it so much more costly to even do. Like, it's already very time consuming to read through this stuff and to make mistakes while reading through it. But if I was trying to guarantee I didn't make any mistakes, it would take an order of magnitude longer, which is why I have to do it this way, because I want to get through a lot of different things, and I can't be focused only on perfection. So I'm basically saying I'm doing a cost-benefit analysis, and I'm like, you know what? It's worth making some mistakes and having stuff come out wrong as long as I can maintain that forward momentum. But I do apologize for incorrect information. In this next module, we have the exceptions. It just declares a bunch of exceptions. This stuff is not that valuable to look at unless you want to understand all the exceptions. And even then, it's usually very hard to really remember anyways. I've looked at tons of different exceptions in libraries, and it's just, you don't really remember a lot of it. And when you encounter them, you just read them, and hopefully they make sense. So that's what this is, and it just defines all these. Then we have a help module. This is, I think, probably for the command line one. Let me just look here. Nope, it doesn't. It doesn't import it. I don't think it imports help. I don't think so. Arc Parser.print help. Okay, so it's definitely different. It's different altogether. All right, let's look through this. What is this about? All right, it has this thing at the top, from future import print function, import JSON, import platform, import sys, import version from PyJWT version, try to import cryptography, import ECDSA, and then have a function, a module function, which is info. Description, generate information for a bug report based on the request package help utility module. And then it packs in, gets the platform info, the implementation info. These are kind of interesting methods to be aware of if you ever want to write a library and be able to introspect the interpreter you're on, right? Like, if you're anticipating that, this stuff probably matters more to you. This platform library, which can tell you all this stuff. It's cool, right? You see CPython here, you see PyPy here, you see these different versions of them. And then so what this is kind of saying is my library, which is PyJWT, it's not mine, but the author, like I was the author, he's saying, all right, this is my library, and this is my dependencies that really matter. I want to know what the platform is. I want to know what the implementation is. I want to know what the cryptography version is, because I need that, and I want to know what my version is. And this is sort of like for troubleshooting, probably. And so if you run this from the command line, right, it's going to basically dump that info. And so it's good for troubleshooting if there's issues. Like, say someone puts a ticket on his GitHub or something, and they're like, I've got this problem, this error. He's going to be like, can you run this command in that environment? And that's going to help him troubleshoot it, because it's like super hard to actually do that when you think about writing a library and you have so many concurrent users with so many different permutations of implementations and whatnot. Here's the Utils module. It's the very last one. You guys have been great. You've made it really far. It imports base64, bin, ASCII, struct. It imports from compat that we saw before, .compat, the binary type, the bytes from int, the text type. And then it tries to import from cryptography, Hmac primitives, asymmetric, utils, decode, DSS signature, encode, DSS signature. It ignores if there's an import error there. Then it defines the force Unicode method we saw. All this does is it takes a binary type and turns it into a string. And if it's a string, it just returns it naked. And if it's neither, it raises a type error. Force bytes is the inverse. If it's a text, it turns it into a byte by UTF-8 encoding it. If it's a binary type, it just returns it as is. And if it's neither, it raises a type error. Base64 URL decode method checks if it's a text type, checks that it can be encoded as ASCII and converts it to that. And then it basically is going to do this remainder thing. Wow, interesting. Okay, this looks like more binary based stuff, but if the remainder, okay, remainder equals the length of the input mod 4. And this is just the length of an ASCII string. So if there's 4 characters, it's going to be like, the remainder is going to be 0, I guess. And if remainder is greater than 0, input plus equals the byte string equals times 4. Oh yeah, this makes sense. All right, so base64 has this thing called padding in it, and it's basically like, what is base64? Well, it's basically ASCII characters. It's 64 different ASCII characters, okay, and it allows you to encode binary data where each one of those characters represents 64 bits, right? Okay, and so when you're decoding it, what you're interested in is basically you need to add to the string equals signs if the entire binary blob, which could be, you know, it could be 63 bytes or something, or man, I'm really messing this up, but basically like it might not all fit in correctly, and so you just pad in these equals signs. The most obvious example I've seen of this is if you ever use like PEM files for SSHing. In the PEM file, it's base64, you know, encoded, right? And at the end, you almost always see these equals, 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 or equals, equals, or equals, you know, that is the padding at the very end of the payload. And you also see it with stuff like if you're given like a secret key from like AWS. So anyways, so that's what that function does. And then it eventually passes it to the base64 library itself with URL safe base64 decode the input. And then the base64 URL encode basically just does the same. It takes the input, base64 URL safe base64 encodes it, and then it replaces any equals signs with nothing. Okay. Okay. And to base64 URL uint, if the value is less than 0, it must be a positive, raise a value error because it has to be a positive integer. And then basically just use that method we declared, I think, in .compat, and you get your integer in the form of bytes. And then basically, if it's equal to 0, then the int bytes is just set to this byte string with, this is an interesting byte string. It's a byte string, but it's not using ASCII anymore. It's using literal hex values. Why? Why does this work? Well, when you think about it, if you use ASCII characters, they're going to fall between values of 0 and like 7-bit ASCII would be like 128, but like 8 bits, which is what this is. It's a byte string, so it's octets, right? That's going to be between 0 and 255, right? So if you just use hexadecimal to declare that, it's going to be equivalent because hexadecimal is going to be one 16-bit thing and then another 16-bit thing, which when you combine them are going to be equivalent. Base 64 URL encode those integer bytes, handling that weird case of 0, which doesn't work with this other method they created. If you do the same thing with from base 64 URL to uint, so it's going to be, yeah. So we're gonna first encode it as ASCII, then we're gonna decode the base 64 URL, have the binary, then we're going to pack it in with struct and have a buffer, and then we're going to, this is interesting. Okay, we're going to convert it to the hexadecimal version. Okay, let's just start from here. 4-byte in buffer, print it as hexadecimal, and then join all of them together with no space, and then convert it to an integer with the second positional argument of being 16, which is probably the length of it. Okay, and then we have the merge dictionary method. If not updates, return original. Okay, and then we have try merged options equals original.copy, merged options.update updates, accept attribute error, value error as E, raise type error, original and updates must be a dictionary. Okay, yeah, it's just running an update that's a little bit more generic and handles some permutations. Okay, the next method is number to bytes, and it takes a number and a variable called numbytes. It multiplies the number of bytes times 2, and then, wow, that's weird. I don't really know how to interpret this that well. Okay, well, it has a variable called padded hex that's using kind of a syntax I'm really not that familiar with. And then it has a variable called big Indian, which is taking that padded hex, encoding it to ASCII, and then using this library bin ASCII and the method a to b underscore hex. This is just like magic that I'd have to look up. I'm not sure what this is doing, but basically it looks like it's just encoding something as big Indian binary. Yeah, it's just taking a number and preparing it in big Indian form, which is network byte order. So it's preparing it to be sent over the network. Bytes to number is just doing a similar thing. It's just the inverse of this. And then dir to raw signature got more. Yeah, so anyways, you get the idea. I'm pretty tired, but wow. So if you guys actually watch this entire video, you've been through a lot of information here. And this is a pretty small library, so we'll see how many of these things I can actually do. I'm going to have to probably prune more of the files and not just necessarily do all of them in the future. But yeah, this has been a review of the PyJWT library by Jose Padilla, version 1.7.0. And if you're interested in more of this like hardcore, super detailed review of stuff, leave no rock unturned type of mentality, check out my other videos. I also am trying to continue adding content to a programming blog focused on the internet and Python and JavaScript. I try and do some like minimal front end development so I can have websites. And so go check out my blog at pyharbor.com. And yeah, thanks.